you see?
Yeah, it's on presenter view.
Yeah. How about now?
Yeah.
Great. So hi, yeah. So I'll be talking about deep learning for musculoskeletal image analysis and visualization. So as Hala presented, we are part of the ARC Training Center for Innovative Bioengineering. And I'm leading the theme of medical imaging, which involves multiple academics, including Professor Jinman, who just gave a talk, Ashley Okuma, who's the co-host, chair of this session, and Professor Dagan Feng. And actually, we have a picture here of our membership, and we've been very fortunate to recruit 3 good team members. We have Dr. Lei Bai, who's also online, and he will be giving a short talk as part of my presentation, and then 2 PhD students, Yuji and Jun Jung. And basically, I'll be talking about the projects that they are actively involved in at the moment. And over the years, we actually built up quite a good network of partners, including Stryker, Think Surgical, which is a Silicon Valley company, Royal North Shore, Microsoft, Westmead, and of course, our Royal Prince Alfred Hospital as our partner. So, artificial intelligence, I think I don't really need to explain this anymore. It's a very topical area. Everyone is talking about AI. But then to me, one of the most important application of it is in medical imaging, because it is this area called convolutional neural network that has really been a breakthrough through deep learning. It's really good with large sets of medical imaging data, including medical images. And so we are working with hospitals and industry partners to develop advanced artificial intelligence technologies to help clinicians to analyze images and plan surgeries. And equipped with the state-of-the-art computing facilities, including computing cluster, proprietary software tools and algorithms, and deep research expertise in medical imaging. Basically, our team takes raw image data directly from PACS in DICOM formats, and then we label it, we do cleaning, we have tools to help you annotate, help you normalize, help you clean up the data so that it can be fed into AI algorithms to build models, design, and then optimize. And then we test the model and we validate if it's practically and clinically relevant and useful through evaluation. We do both retrospective as well as help with deployment to our clinical partners. So AI is such an exciting field. You know, I always talk about it was only in 2016 when major publication appeared in Nature and in Science saying that deep learning can help or can be equivalent and match the level of clinical clinicians in evaluating and in assessing medical images. And then in just a few years, you know, we have many startup companies getting FDA approved for computer-aided diagnosis software algorithms and software tools. And then just last year in RSNA, there were over 170 vendors and companies all providing some sort of AI-based image processing softwares and solutions. And I expect this year to grow and continue to sustain that growth. And then any world market analysis report would indicate that there's a sharp increase in the use of AI and these relevant technologies into the medical imaging market. And MSK is no different. There are companies that's designed and constantly building solutions for musculoskeletal area. And so if I look at specifically on what we do, our 4 projects that I'd like to talk about today, one is on modeling tumor growth and spread in PET-CT imaging data, and we apply that to musculoskeletal area of the cancer. And this is in collaboration with Professor Marco from RRPA. And then bone tumor segmentation from multimodality MRI, and this is in collaboration with Stryker and also with Professor Peter Chung at University of Melbourne. And I have very briefly talk about preoperative orthopedic surgery planning, which is a new project that we are starting to initiate with Think Surgical. And then post-surgical total knee arthroplasty analysis together with Professor Bill Walters and Ghent University. And so I will really quickly just provide a teaser and then open up to discussions if you're interested in our session afterwards. And so what we do is we grab images, we do AI deep learning to annotate, to segment, to classify, to understand the images, which then gets used for providing visual augmentations to clinicians during surgery and during part of decision support. And so the first project is distant metastasis prediction in PET-CT soft tissue sarcoma. And this is the work that's done by our PhD student, Igor. And he's very happy these days. He's been doing really well with publications. So for this project, our aim is to research focus on early detection of metastasis disease in patients with musculoskeletal tumors. Early detection is important for effective patient management, and our objective is to develop, evaluate, and disseminate software for AI-based radiomic algorithms for early detection. And we will build algorithms as well as curate data and make that public, so increase our research community. But what's really interesting is that our research and our publication has shown that if we can carefully and accurately characterize tumors from a PET-CT scan, we can predict relatively with good confidence if it will become metastasis, which means if it will spread to other parts of the body. PET-CT is unique in that, where we have both functional information from PET and anatomical information from CT, and deep features combined together has been really good at prediction. And so we apply the concept of radiomics, which is a combination of visual features from images, which may not be that easily, or which may not always be used by clinicians in interpretation. So using machine learning, using our algorithms, we look at every feature that's available in this multimodal data. And we try to correlate tumor image features with survival rate, with distant metastasis and other things. And so this is, what we are very good at from being from School of Computer Science. Given this problem, once we know what we want to do, we build fancy algorithms, and this is just the architecture that Igor built. And I think this one was published in MICI this year. And the results are very promising. So when it comes to trying to detect distant metastasis, we are getting state-of-the-art results compared to all other published algorithms, both in 3D and as well as in 2D. And we are currently extending this to become even more accurate by exploring what we call neural architecture search, which is you let the machine search for an optimal architecture to solve a specific patient's imaging problem. And of course, this is still an engineering paper. We got a long way to go until we actually validate this to be clinically relevant. But with accuracy that we are getting now, we are very confident that this can become a valuable decision support system. The second project I'd like to talk about is advanced volumetric visualization, and this is the work that's done by our PhD student Jun. And most of this work I'm presenting is the work he's done before he joined here as an MPhil student, but he was still working on our projects. And so the aim of advanced 3D visualization is that, and also hologram. I'm a big fan of hologram, which is holographic augmentation of virtual objects into a physical environment. Our aim is to produce new 3D rendering algorithms that enable clinicians to view anatomical characteristics of the defect without the noise and obstruction inherent in medical images. And then really what we're trying to do is integrate deep learning. So automatic image processing, automatic labeling, automatic detection of important sites, and using that to provide visualization such as for surgery, and providing an augmentation of these information into actual part of when they're doing surgical operations. And all of it is to improve efficiency and effectiveness. And we are in a process of measuring and evaluating that. And so just a few examples. This is a video. Yeah, this is a video. So typically when you interpret PET-CT images, you get your cross-sectional views. In this particular example is coronal view, and then you will navigate to see where the tumor is. But then with our algorithm, if you can detect where the tumor is, and we have algorithms to do that, then that information can be used to automatically produce relevant and informative volume rendering, which means you can look at just images like this immediately, rather than trying to typically, which is with a conventional vendor software, you need to spend time building visualizations like this. But our algorithm, by understanding what is available in the 2D DICOM images, can produce renderings like that. And then the other example I'd like to demonstrate here is the entire pipeline. So we have technologies where we start with segmentation. So in this case, it's to understand refracture or bone. So we can segment the CT of the patient, produce 3D rendering, and then use HoloLens, which is a head-mounted augmented reality device, so that you can overlay your CT preoperative data into actual patient. In here, we use a mannequin, but the whole idea is that we can overlay it on a patient. And this is just another video where, this is a real patient data which we process, and then you can overlay. And we use the rib here because it looks the best, but we have examples where we are doing it on the knee and where we are doing it on the hips as well. And so now I'm gonna pass.
Sorry, Jinman, we are a bit out of time. Sorry, if you could try and wrap up, that would be great.
Okay, all right. Sorry, then I want to ask Billy to talk, but this is quickly on a project on segmenting MR bone tumors, which has been extremely difficult actually. And we are trying to work with our partners in both Australia and in Hong Kong to collect enough data to build up our model. I mean, if we build it, you'll be the first one to do that. And yeah, so these were just some examples of how complex it is, but then how our algorithm is starting to understand. And so we built up a tool to help not only give automatic segmentation, but then use it to refine it so that we can continue to build up our training data set. So thanks.